Welcome to Programming in C++ Part 2. Chapter 18, Stacks and Queues Study Guide. Please hit the like button, leave a comment, and subscribe to the channel. Suppose that you have a program with several functions. To be specific, suppose that you have functions A, B, C, and D in your program. Now suppose that function A calls function B calls function C, and function C calls function D. When function D terminates, control goes back to function C. When function C terminates, control goes back to function B, and when function B terminates, control goes back to function A. During program execution, how do you think the computer keeps track of the function calls? What about recursive functions? How does the computer keep track of the recursive calls? In Chapter 17, we designed a recursive function to print a linked list backward. What if you want to write a non-recursive algorithm to print a linked list backward? If you try to add a new item to a full stack, the resulting condition is called an overflow. Think of it like a pile of books. You add or push a book on top and take, or pop, the top book off. This section discusses the data structure called the stack, which the computer uses to implement function calls. You can also use stacks to convert recursive algorithms into non-recursive algorithms, especially recursive algorithms that are not tail recursive. Stacks have numerous applications in computer science. After developing the tools necessary to implement a stack, we will examine some applications of stacks. The push operation of a stack adds a new element to the top of the stack. Now on to the next section, right after this. Because all the elements of a stack are of the same type, you can use an array to implement a stack. The first element of the stack can be put in the first array slot, the second element of the stack in the second array slot, and so on. The top of the stack is the index of the last element added to the stack. In this implementation of a stack, stack elements are stored in an array, and an array is a random access data structure, that is, you can directly access any element of the array. However, by definition, a stack is a data structure in which the elements are accessed, popped, or pushed at only one end, that is, a LIFO data structure. Thus, a stack element is accessed only through the top, not through the bottom or middle. This feature of a stack is extremely important and must be recognized in the beginning. We have seen that the value of stack top indicates whether the stack is empty. If stack top is 0, the stack is empty. Otherwise, the stack is not empty. Next, we consider the operation is full stack. It follows that the stack is full if stack top is equal to max stack size. Copy constructor is called when a stack object is passed as a value parameter to a function. It copies the values of the member variables of the actual parameter into the corresponding member variables of the formal parameter. Recall that classes with pointer member variables, the assignment operator must be explicitly overloaded. Now that you know how to implement the stack operations, you can put the definitions of the class and the functions to implement the stack operations together to create the stack header file. Suppose that the name of the header file containing the definition of the class stack type is myStackH. We will refer to this header file in any program that uses a stack. That covers Chapter 2. Now on to Chapter 3 right after this. Because an array size is fixed, in the array linear representation of a stack, only a fixed number of elements can be pushed onto the stack. If in a program the number of elements to be pushed exceeds the size of the array, the program may terminate in an error. We must overcome these problems. For example, here is a stack implementation hash include std stack mystack push 10, mystack push 20, mystack.pop / removes 20. And here is a queue implementation hash include std queue myqueue push 10, myqueue push 20, myqueue.fr on tu / returns 10 myqueue.pop / removes 10. These snippets demonstrate the ease of using C++ standard library containers for managing stacks and queues. ABCD plus C plus D. An infix expression is one in which the operators are written between the operands. We have seen that by using pointer variables, we can dynamically allocate and deallocate memory, and by using linked lists, we can dynamically organize data, such as an ordered list. Next, we will use these concepts to implement a stack dynamically. Many compilers translate arithmetic expressions into postfix notation, and then translate this expression into machine code. The operation initialize stack reinitializes the stack to an empty state. Because the stack may contain some elements and we are using a linked implementation of a stack, we must deallocate the memory occupied by the stack elements and set stack top to null pointer. Sort the stack is not a basic stack operation. If we compare the push function of the stack with the insert first function discussed for general lists in Chapter 17, we see that the algorithms to implement these operations are similar. Pop removes the top element of the stack. Note that the class linked list type is an abstract and does not implement all of the operations. However, the class unordered linked list type is derived from the class linked list type and provides the definitions of the abstract functions of the class linked list type. Therefore, we can derive the class linked stack type from the class unordered linked list type. The definitions of the functions to implement the stack operations are also given. In a queuing system, the time it takes to serve a customer is called the transaction time. A queuing system consists of servers and queues of objects waiting to be served. That's all for Chapter 3, folks. Now on to Chapter 4, right after this. This section discusses another important data structure called a queue. The notion of a queue in computer science is the same as the notion of the queues to which you are accustomed in everyday life. There are queues of customers in a bank or in a grocery store and queues of cars waiting to pass through a toll booth. Similarly, because a computer can send a print request faster than a printer can print, a queue of documents is often waiting to be printed at a printer. The general rule to process elements in a queue is that the customer at the front of the queue is served next, and when a new customer arrives, he or she stands at the end of the queue. That is, a queue is a first-in first-out, FIFO, data structure. The isFullQueue function always returns the value false in a linked queue. Queues have numerous applications in computer science. Whenever a system is modeled on the FIFO principle, queues are used. At the end of this section, we will discuss one of the most widely used applications of queues, computer simulation. First, however, we need to develop the tools necessary to implement a queue. The next few sections discuss how to design classes to implement queues as an ADT. In a queue, elements are deleted from the end called the front. A queue is a set of elements of the same type in which the elements are added at one end, called the back or rear, and deleted from the other end, called the front. For example, consider a line of customers in a bank, wherein the customers are waiting to withdraw/deposit money or to conduct some other business. Each new customer gets in the line at the rear. Whenever a teller is ready for a new customer, the customer at the front of the line is served. In a linked representation of a stack, the stack is considered to be full only if the computer runs out of memory. Let's take a quick break. We will be right back after this. The rear of the queue is accessed whenever a new element is added to the queue, and the front of the queue is accessed whenever an element is deleted from the queue. As in a stack, the middle elements of the queue are inaccessible, even if the queue elements are stored in an array. From the definition of queues, we see that the two key operations are add and delete. We call the add operation add queue and the delete operation delete queue. Because elements can be neither deleted from an empty queue nor added to a full queue, we need two more operations to successfully implement the add queue and delete queue operations. IsEmptyQueue checks whether the queue is empty, and isFullQueue checks whether a queue is full. A technique in which one system models the behavior of another system is called simulation. Before giving the definition of the class to implement a queue as an ADT, we need to decide how many member variables are needed to implement the queue. Of course, we need an array to store the queue elements, the variables queueFront and queueRear to keep track of the first and last elements of the queue, and the variable maxQueueSize to specify the maximum size of the queue. Thus, we need at least 4 member variables. A prefix expression is one in which the operators are written before the operands. From the definitions of the functions to implement the queue operations, it is clear that the linked implementation of a queue is similar to the implementation of a linked list created in a forward manner. See Chapter 17. If you try to remove an item from an empty stack, the resulting condition is called simulation. There you have it, stacks and queues. We will finish up right after this. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. If you are unable to do that, you will need to log in. Creating a YouTube account is free and takes less than a minute. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. Have a wonderful day.